Hello everyone, welcome to Unit 6, Lesson 8, Take a Breath Notes. By the end of this, whoops, that should be the focus question. Oh well. You should be able to answer the focus question, what is the ideal gas law, and what variables, including units, are involved in the calculation? So for the do now, you should describe how you determine the volume of a breath of air. Name 4 factors that might affect the volume you measure, as well as discuss what do you need to know in order to determine the number of molecules in a breath of air. So for this first one, you should pause the video and then answer in your do now spot, and then we'll come back. For this one, when we determine the volume of a breath of air in the lab specifically, you're going to do it by volume displacement. So when you do the lab, you're going to have a bottle that is going to be, it's a 2-liter bottle, submerged in water. It's kind of hard to figure out where things are. So what you are going to do, because unless it's completely filled, you're going to have a little bit of air once you fill it up with water. So you first are going to have water here in the tub, and then before you flip it upside down, you're going to fill this 2-liter completely full with water. So it should be 100% full with water. You're going to use your finger to seal it and then put it into the tub submerged below the water. And if you do this right, you should not lose any water in the top. Okay, then you are going to, while this is sealed, carefully thread the tubing provided into the thing here. And it's not going to be a tight thread, that's okay. And then what you are going to do is you are going to put a straw, these are available at my front lab station, in here, because you're going to put your mouth on the straw. And I think I have bendy straws, but who knows what I got. Then you are going to blow air into this straw, and it's going to push air into this, and the water level will drop. If you do a normal breath, it should drop somewhere. If you're a swimmer, it'll drop a lot more than if you play soccer or something. This air here that you blew in is your one breath. But it's hard to determine what that is. So you're going to take a marker or a Sharpie, and you're going to mark what that level is. Okay, the Sharpies are going to be all on my front lab station as well for you guys to grab. You're going to mark that. Then you're going to reset everything, and you will fill with water. So you're going to have this bottle that you marked on. And there might be other marks, just remember which one's yours. You marked on it somewhere, you're going to fill this with water to that line, and then you're going to use a graduated cylinder, and I should have 1-liter graduated cylinders, to pour that water in there and measure it in milliliters. Okay, so once again, you're going to fill the tub about halfway full-ish with water. Then fill the 2-liter bottle completely full with water. Use your hand to cover the top and carefully flip it and submerge it in the water, being careful not to lose any water. Then thread the tubing, attach the straw, and blow 1 normal breath into that 2-liter. Whatever the air lands at, you're going to mark with a Sharpie, pull the bottle out, fill with water just to that line, and transfer to a graduated cylinder to measure. There are a bunch of different factors that might affect the volume. If you lost any water when you were flipping it, that might happen. If there's any leaks here, some of that air might escape, so you might want to make sure it's sealed off pretty well. If you squeeze the bottle, that could affect your volume. And then your daily activity, how active you are, what kinds of activity you do. I mentioned swimmers versus soccer players versus moms like me. My lung capacity is not going to be anywhere near what a swimmer might do. A musician, somebody who plays a wind instrument or a horn instrument where they have to blow into, will have a larger lung capacity because of the type of activities that they do day to day, like blowing into the instrument, than someone who does not do that. Swimmers, because they have to hold their breath for long periods of time, typically have much larger lungs and therefore will have more air in one breath. Okay, and then once we know that, like, we need to determine the number of molecules, what's related to a molecule that we have used in the past. We got to think back about a month. And we would then realize, like, if we looked at our mole map, we would see that particles can go to moles. So if we know the number of moles of gas, we can use Avogadro's number, where 1 mole is 6.02 times 10 to the 23rd particles or molecules, to change moles to molecules. And that's what we're going to look at today. How can we figure out the number of moles in our gas? So for the lab, one person will do the breathing for lab due to time restrictions and the number of straws I've got. Straws are at the front as well as Sharpies and everything. Make sure you are washing stuff just so that way it's clean. A little bit of soap and some like scrubbing with your hands is sufficient. Rinse. And then once you are done washing stuff and you're ready to end the lab, you will hang everything back on the drying racks, okay? Or on the drying racks to begin with. Cool. Okay, make sure you clean up after yourselves when you are done. And you're going to do all the data and everything on page 26. Okay, here we are for notes. The ideal gas law is a result of combining the combined gas law with Avogadro's law, which we have not discussed, but Avogadro's law states that the number of moles of gas is directly proportional to its molar volume. Okay. This allows us to calculate the number of gas particles, or moles of gas, present at any specific volume, temperature, and pressure. So unlike the others where we had 2 sets of variables that were the same measurement type, but at different points in time relating to each other, ideal gas law looks at only one specific point in time, okay, and relates all of those variables to each other. So we remember that P is pressure. And typically we have units of atmospheres that we have used in the past, but you may see torr or you may see PSI. There's a couple others, but those are the most common ones. Another one is kPa, kilopascals. V is volume. We have seen milliliters and liters. N is moles, right? We know the variable for that, or the units for that variable. And then T is temperature. And remember, for gas laws, we only use Kelvin. R is the new one, and this is our gas constant. And it has a specific value depending on the units for pressure. So for the gas constant, we are always going to use liters for volume, and typically we are using atmospheres for the pressure. If we use kilopascals, it will have a different value and it's on a different slide. But for this one, R, we typically use atmospheres and liters for this. It's 0.08206 atmosphere liters over mole Kelvin. And because we don't have a lowercase k, we are actually using an R. And this is true for any ideal gas as long as it's got these units. Okay, it's our way to make sure that all of these values are proportional to each other and that the math works out. So it's a constant to help the math work out. That's the only reason we have it. And it's for ideal gas law for any one point in time. Our proportionality constants from our previous gas laws are for variable points in time, and so that is not one specific number, but will change. Because ideal gas law uses the gas constant R, it's one specific point in time, and so it has one specific gas constant that is based off of the units for the variables in that. The R is the same for all gases, but you need to make sure that you are using the correct units. The only other ones that we will use consistently in this class is this gas constant for kilopascal. So there's only two. I will give you whichever one you need when you need it, okay? But just check, are you using atmospheres? So remember, you could be 0.08206 atm liter over mole Kelvin, or kPa liter over mole Kelvin. So you just got to pay attention to what units for pressure and make sure the rest of the units are matching. So here we go. Let's do a practice problem. You cap a 1 liter plastic bottle on a mountaintop where the air pressure is 5 atmospheres and the temperature is 298 Kelvin. How many moles of gas are in the bottle? So here's my V, here's my P, here's T, and then moles of gas is N, and that's my unknown. Okay, so that tells me I'm using the ideal gas law. And my R has to be the one that contains atmospheres. So my R is going to be 0.08206 because that is the one that had atmosphere. Okay, now I'm going to substitute in for all my variables that I was given. So 0.50 atm times 1 liter is equal to N, that I do not know. R you will always know, it just might change depending on your units. And then T was 298 Kelvin. Okay, so then using our calculator, we're going to simplify this, and we end up seeing that atmospheres cancel, liters cancel, and Kelvin cancels, with moles being in our answer. Okay, so simplifying, we see that the left side is 0.5 is equal to, and then 0.08206 times 298 is 24.45 and some change, 1 over mole, because the mole's in the denominator, times N. So then I'm going to divide both sides by the number attached to N. Okay, and so this cancels, and if it's in the denominator, it flips up to the top. So then I'm going to do 0.5 divided by the 24.45, and I end up with N is equal to 0.0204 moles of gas. And that's all we do. A little bit of algebra. Okay. So, I don't know why that says 18. I guess that should be 24. Answer the focus question on page 24 using complete sentences. What is the ideal gas law, and what variables with units are involved in the calculation? Like, what is it? How do we use it? Why is it different and important from the other gas laws? Thank you guys for tuning in.